Let's go ahead and get started. So today we're going to be talking about analyzing multi-species data and using multivariate autoregressive models to understand the dynamics of the system, understand the interaction strengths, and understand how those interactions are changing over time and how that might lead to changes in the stability of the system. This is a really rich body of literature, largely in freshwater lake plankton systems, but it's used in other systems also. And Mark's going to talk about a ocean reef, a kelp forest community analysis partway through the lecture. Hey, come on. There we go. Okay, so today I'll introduce you to univariate and multivariate Gompertz models, which is basically a multivariate autoregressive lag1 model, and introduce you to how those are used to model density dependence and interactions. And then Mark will talk about a kelp forest example study. I'll show some examples with two species models, and then we'll talk more about dynamics of these large community systems and understanding how what you get out of the B matrix for understanding the dynamics of those systems. I'm going to be, I'm going to be talking about mean-reverting processes, and that's a jargon for a process that reverts back to a mean. So here's really an example, reverts back to a mean. Here it's a bit looser, it reverts back to a mean. And density dependence is this classic ecological process that causes mean reversion, returning back to some level if you get pushed away from that level. The classic mean reverting process in the physics literature is the Ornstein-Uhlenbeck process. And the Gompertz that we'll be studying is a discrete time. It's kind of like a discrete time version of that. It's not really a version because it's discrete time, but it's sort of the analog of the classic mean reverting process, but in the discrete time realm. So this is what a univariate Gompertz model looks like. You've seen it before. It's just a lag1 autoregressive process. We've got the autoregression here. The terms here, though, mean have an ecological meaning. The B is a term that indicates the strength of density dependence, and the U is the intrinsic rate of increase. And you'll see where that comes from in a moment. Okay, so let's think about how you might write an exponential growth model, not in log space. Now the end is your abundance, and so your exponential growth model would look like this. Your abundance at time t is the abundance at the previous time step times your growth rate, right? Standard exponential growth. And in general, when we make that into a density-dependent model, we replace this, which is this constant growth, with some function of the abundance. And in particular, as the abundance goes up, this growth rate is going to go down. It's the idea of the density dependence. A little more specific type of that function is if we took this exponential growth function, so we had u here, and then we had u plus some function. And now this is going to go negative as this gets really large. So that the result of that is that as this gets really large, this is going to get really small. And conversely, as this gets get really small, we're going to have this go typically to 0, so that as n is small, u, this function goes to u, so you get back to exponential growth. That's not always the case. We obviously could have density depensation, where you have this case where the opposite happens. As the population gets too small, growth rate goes negative again. But in general, what you would have is that as the population gets really small, this drops out, and you go back to exponential growth. The Gompertz model falls into that class. I'm writing this in the non-log space. I'm going to show you how this will end up being that really simple Lagrange autoregressive model in a moment. Okay, well, let's imagine that we had this function for our density dependence. So we had u plus this function right here. And what does that look like graphically? This right here. So what it does is that as log n is small, then the growth rate is greater than 1, so the population would increase. And then when it's smaller, when it's larger, then the growth rate becomes less than 1, and so the population would decrease. And where it crosses 1, that's where the equilibrium is. In this case, to make this plot, I happened to use, what did I use? I used u equals 2, and I used b equals 0.8. So that's the equilibrium is u over 1 minus b, so it would be u divided by 0.2, so that's why it came out to be 10. But this is the general form of what this looks like. It's this kind of this exponentially declining shape. So that's the form of the density dependence we are assuming. And if we take that, and we just do a little bit of algebra, we take the log of both sides, this thing falls out here, and then we start moving things around, then we come out with the log of t equals u plus b times the log of n at t minus 1, and we substitute x for log n, so we're working in log space, and we get that. So that just shows you how this simple AR model is related to this type of density dependence model. You have the growth rate being lower as you pass some equilibrium level here. And then here it's higher. So this particular density dependent model has some particular properties. We're interested in this region here where, particularly here, where b is between 0 and 1. And in that case, there's an equilibrium here. And if you start away from the equilibrium, what happens is it'll go up towards that equilibrium. If b were between 0 and negative 1, it would still go towards the equilibrium, but it does it with a 1-point cycle like that. So one thing to note about this, which is a little different than some other density-dependent models, is that it approaches equilibrium smoothly. And there's a point equilibrium. It's not a cycle equilibrium, it's just a point. So it doesn't go like that. Some other density-dependent models would do that. This one doesn't. It goes to equilibrium smoothly. If you add some noise to that, so let's see, this model here, I didn't have any noise. I showed those plots were for this model. But if I add some error there, so I make this stochastic, So here's our two cases again. So this is this, the red is 0.9. 1 is a random walk, that would be equals 1, but let's look at the red one. You see how it kind of cycles here. And if you start away, it'll kind of go up and then it'll kind of head towards that equilibrium and then cycle around it. And when you have a stochastic process, when you talk about the equilibrium, you don't have a point equilibrium. Instead, you have an equilibrium distribution. So that distribution, say, let's say if B equals 0.6, that distribution has a particular mean. In this case, U was set to 0, so the mean is 0. That distribution has a particular variance. If we have a B that's closer to 1, it still has a distribution. In this case, U was 0, so the mean is 0. But you can see the variance is larger. So here's the variance of that one. That's the distribution. So those are the two key things that describe this stochastic equilibrium. It has a mean, it has a variance. Okay, so I mentioned those main properties, point equilibrium. Another feature of this is that even though this is a specific type of density dependence, a specific form of that that line that I showed you of how U, the growth rate as a function of population size, the particular shape of that, it can be seen as a locally linear approximation of many other types of density dependence. So what does locally linear mean? That means that as long as you don't change the population size too much, then it still holds. So like imagine you have some like curve like this, and the idea of locally linear means that, well, if I just look at a small portion of that, I can approximate that with this straight line. So here's the idea here. So in the log space, this the model that we're using are these linear lines like this. And let's say we had a different density dependent function and it actually looked just like this nonlinear thing. Well, even though that's the case, the Gompertz model can approximate that with this sort of as these linear lines here. So it's not quite like that, but if we had different Gompertz models in different portions of the abundance level, we can still approximate that. So you're going to run into this idea when you see the applications where people are using this Gompertz model for populations where they're the populations are changing size dramatically. And what they're doing is they're using a time-varying Gompertz model. And so they're still using the same model, but that B matrix is going to be different when population sizes are in one place, and then there's going to be a different B matrix in another place. And they're going to be trying to estimate what these B matrices are. So they're using this idea of this linear approximation. Okay, so what we're going to be talking about today is be using examples where some of the examples will be assuming no observation error. I say some of the examples because Mark's going to be talking about a study where they did include observation error. But in a lot of the studies in the literature, people are using this on plankton data, and they assume that there's no observation error in the data. And There's a lot of research trying to understand what that assumption does. And what it does is it creates this spurious density dependence. And let's see if I have a picture of that. Yeah, okay, I don't have a picture. What it does is it shrinks your B estimate. And if B is really small, that means that you come back tightly back to the equilibrium. And if B is close to 1, you wander away. So 1 would be no density dependence. And then B close to 0 would be like really tight density dependence. If you have observation error in your data and you don't account for that, what happens is you get that B estimate smaller. It looks like you have density dependence when you don't. And MAR models with an observation process, which would be MAR state space, allow you to incorporate that and deal with that problem. Mark's going to show you one example, and there's a lot of literature on how to deal with this. And the one of the most powerful ways to deal with this is simply to have replication. You have 2 different sites where you can argue, believe that they have the same B matrix, or it's reasonable to assume that they have the same B matrix, and they have the same process variance, because it's sort of similar processes that are affecting the systems. And then you can use those as spatial replicates and sort out your observation error. And you've seen with the Mars models, with using them for different sites, how you can have different sites. And so you have that observation model with different sites, and each of those sites can be measuring the same process, or they can be measuring processes with the same parameters. It's actually what you're going to do when you replicate in a community system. So this would be like you have, let's say you're looking at a tide pool, and you have the community and or 2 lakes, let's say 2 lakes. And they have very similar communities. They're very close to each other, but they're not connected by water. So you can assume, you choose to assume that the B matrices are similar species, the Q matrices are similar. And then you have, your 15 species in one and your 15 species in the other. So those each go into your observation matrix, which is now going to have 30 rows. Right? Okay, so let's see an example with a simple 2 species example, predator-prey interaction. In chapter 14 in the Mars manual, we go through an example with moose and wolf in Isle Royale. So looking at this long-term data set that they have. And you set up this 2 species example like this. So it's still a Gompertz model, but now we have 2 species. So you have the moose at time t. We're working in log scale space. So that's the log abundance or abundance index of the moose. We have their intrinsic rate of increase. Now we have the effect of moose on themselves, so density dependence of the moose. Now we have wolf in this also. So now we have the wolves showing up there, that's the XW, and we have the effect of wolf on moose. We have the same equation for the wolves. So there's the wolves, rate of increase, the effect of wolves on themselves, and then we have the effect of moose on wolf. So this should be positive, and that should be negative. Let's look at this in nice compact matrix form. So there you have it. So this is your X matrix that has your abundances of the 2 species. And now you have your B matrix, which is your interaction matrix. On the diagonal are the self interactions, so the effect of moose on moose, and wolf on wolf. And then on the off diagonals are the interactions, the effect of wolf on moose, and the effect of moose on wolf. So this matrix captures both interactions, intra and intra-specific interactions. You can add covariates to this, and that's really powerful because if you think about a community, you have the community varying because of these interactions. So wolf go up, that drives the moose down, so that's causing some interactions. But on top of that, you have that both of them are being affected by these environmental covariates. And often what we want to do is we want to tease out how these environmental covariates are affecting our species. And how we do that is we include the covariates in our process model. And so let's say we had 3 covariates. Now we can model the effect of covariate 1 on moose, 2 on moose, 3 on moose, and then separately the effect of 3 on wolf, 2 on wolf, and 1 on, it should be not 1 on 2, that should be 1 on wolf. Okay, so as I mentioned, chapter 14 goes through an example to walk you through analyzing this time series with the model I just showed you and estimating out those strengths. And what you'll see is that if you don't include the environmental covariates in the model, your interactions don't really make sense. You have like your wolves are having a positive effect on the moose, which is not what you would expect. But if you include the covariates that are known to be very important, which is the winter snow depth and the summer heat / precipitation, then the interactions that you get start to make sense, and the effect of these covariates make sense. Meaning those are what the biologists are seeing in the field. So they see that if it's really wet summer, there's lots of ticks, and this has a big effect on the moose. Doesn't really have an effect on the wolves. And you can tease that out with just by analyzing the time series data here and the time series on these covariates. So that's kind of cool. You can pull that out.
Actually, before you go on,
Yeah.
Is everybody familiar with that study in general? Do you know that it turns out that climate change is actually uncoupling all this because there's not enough winter ice? The wolves migrate from Canada on a regular basis over the ice. And so now the wintertime ice is not staying around long enough that they don't have as much population exchange from the mainland. The wolves, so the moose can swim if they want and will. But yeah, I remembered reading something about that recently, like within the last year. It's kind of interesting. And I think now they're actually reintroducing some wolves to the island, taking them from somewhere else.
Yeah, maybe Northeast Washington.
It's somewhere in Canada, I can't remember.
Yeah. Yeah, it's a really remarkable data set. I mean, this is, when I downloaded this, that's 50 years, now we got another 10, so 60 years of long-term data.
I feel like the other popular story I read about climate change was that it's causing increasing tick outbreaks in, I forget what season it is, but basically you think about that as like the density dependence of wolves on, or I'm sorry, moose on moose is going to be increasing over time.
Mm-hmm. Yeah, that says summer precipitation is associated with tick outbreaks.
I was just trying to figure out which line is which.
The moose are dark.
Yeah, these are the wolves. Yeah. And then these had
That big like an outbreak.
yeah, it was like outbreak was it? It was some sort of disease. Yeah.
I have a question. So if adding different covariates drastically changes the interaction effects, how do you like settle on a model or like settle on covariates to include and like what you think is actually the interaction effects?
I'll touch on that at the end, where I touch on model selection. But in order to do that process of model selection, you have to put the covariates into the model. And so you do need to know biologically a lot about the system to know what sort of covariates to include. So that, it just depends on what you're studying. Like, so if you're working in a plankton system, yeah, okay, temperature's surely important. Nutrients, well, we know the nutrients are important. Salinity, maybe not, but that's easy to measure. It's often included. It's, I think it's, doesn't, I feel like it's been rarely found to be an important driver. Yeah, yeah. Yeah, so that sort of thing.
Eli alluded to several years ago, a group of us did a review paper on this. Most of these types of studies now have got plankton systems, primarily in freshwater.
Yeah.
Some of that was sort of the genesis of it. Models were developed largely at Wisconsin. So we're doing a bunch of that stuff anyway. So there's no good answer to it. I mean, I think what Eli was saying before, if you get you're looking at those coefficients, some are predator prey, some are competition. If you get funny looking, it's like, oh, there's a negative effect of prey on predators, that seems kind of weird or positive, but then chances are you're missing something in the analysis. If you have that, great. But there's no silver bullet. There's no real answer to say, oh, I'm done, I got the ones that make sense. It's mostly just being a good ecologist and saying, okay, these are things that, for first principles, should happen. Something will jump out, as Eli said. You may estimate essentially no effect of temperature on something.
Okay, so that's two species example. Okay, so what about when we have much larger models? Well, we can still do the same thing. Let's see. Oh, I don't have that. Okay. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So now we would have a B matrix that's 13 by 13. But the same principles apply. And we can start to understand this community and how, what these different strengths are. Each arrow here would represent one element in the B matrix. So this one here, this arrow here, is the effect of Daphnia on Oscillaria. It's actually 2, and then it would be the effect of Oscillaria on Daphnia. I said that wrong. Oscillatoria on Daphnia. Okay, so that's 2 places in the matrix. We can also, in addition to estimating the strengths of all those little lines, the size of those lines, we can then use that estimated B matrix to quantify stability. I'll show you examples of that. And then lastly, what you're going to see is how do you use those models to start pruning that vast web of all those like interactions. Like there's a lot there. Well, which ones are really important? How do you do that? You mentioned the covariates. Well, you can imagine you have your covariates here. Let's see if in this picture I have more. I only have total phosphorus there. So in this figure, there's just one, but this one has lines to 5 different, is that 5? Yes, 5 different species here. It doesn't have lines up to here because, no, it doesn't affect these. Okay, so this is your bottom of your community. your phytoplankton and your phosphorus is affecting those. But which of those lines is important? Are they all important? Maybe none of them are important. So that's where you get in that model selection. You prune this out and then discover, for example, that what's really happening is that phosphorus is like a big, driver for this species, and that's why phosphorus is having these really huge impacts. Is it's coming through this species here, and then this species has really strong impacts. So it's giving you some really new insights into what's going on with the dynamics. So now we're going to go into a specific. Oh wait, no, not example. Okay, almost, Mark, almost, very close, very close. Okay, so when you have this model, this is what it looks like. You've been working with this. It's the exact same model that you've been working with, except now we're really focused on this B matrix. This is what we're trying to estimate, whereas in most of our other examples, we remove that from the model. We're modeling a random walk, or we are modeling that as just a diagonal. So that means there's only effect of X on itself. But now we're estimating all the elements because we have interactions between all the species, and these are our species. We also are estimating the C, but today I'm really going to focus on that B. We have our observation model there, and you could model like this and just use this multivariate normal. But you could use any other observation model. Mark's going to show you an example where they had data that had a lot of zeros, and they used a zero inflated model. When you have that large B, so this is what it looks like. These are the interactions with yourself. And one thing to keep in mind is that on this diagonal here, if this is close to 0, strong density dependence, close to 1, no density dependence. And that's a little different. It is different on the off diagonal. So in the off diagonal, positive would be a positive effect. Negative would be a negative effect. If you set interaction to 0, it means there's no direct interaction there. There could still be indirect interactions, right? But there's no direct interaction. As I said, widely used to study lake ecosystems. And this is the review paper that Mark was mentioning. We have a lot of papers there, so if you're interested, this is a good place to start to learn about the literature.
Lake Erie?
That is Lake Erie, yeah, and that's a bloom. Yeah, that's a phytoplankton bloom in Lake Erie, and actually this is, I believe, an Arctic. It's not a lake; it's Arctic. I think it's from Alaska. I was trying to find a nice picture that showed a whole bunch of different species from a lake. Go find one. One of the most classic applications of MAR models is in studying what happened to Lake Washington. There's a long series of papers on this, and as you know, back in the 50s, all the way up to the early 60s, Lake Washington was really vile because they were dumping raw sewage into it, and surprise, surprise, that had really negative consequences. So these huge, lots of algae, lots of very stinky, and there's a big uproar about it. Finally, they divert the sewage in the early 60s, and it takes a while, a good, what was it, almost 10 years, not quite 10 years. And so here's the Secchi score. So it's very, very, very cloudy here. And then here's the diversion right about here. Diversion's happening around here. It's still cloudy, and then, whoa, it takes a good almost 10 years for the lake to clear up. And around that time, you see Daphnia, which was largely not present before. Daphnia appears, and this oscillatoria, which was very present, decreases. Okay, so let's jump in and see an example of that that Mark has been involved with, studying kelp forest ecosystems. Okay, you'll have to guess what the slides are. I cut out kind of everything with this way. He gave me slides, and I took them, and I was like.
She said, "Just give me some slides," so I did. So anyway, that's this is going to be one of those, right? I'll now just.
So you can focus on the.
Who knows what we're going to get today? This will be really exciting. Wow, this is a project that Eric and I have been working on for far too long. One of these days, yeah, we'll turn it around. And so Eric and I started messing around with these models that I'll talk about, and we were hunting around for some data sets to use. And at the time, we were going to use a data set from northern Wisconsin, where at the LTR site there's a lake that they had put a large curtain through the middle of to divide it, and they acidified half the lake to simulate acid rain. And they took the pH down to like 4.5. I mean, it was amazing. It just so that the plankton community had completely been re-altered and stuff, and then they took the pH back up to show recovery and stuff like that. So we were going to use this. Anyway, about that time, a data set was published on this massive monitoring effort that's been done in Southern California. I'll talk about in just a minute. So we decided, well, we'll apply these models. So that Eric and I don't know anything about kelp forests or fishes. I guess this is a fish that lives in kelp forests.
It's from the sanctuary.
So anyway, Steve Katz is a colleague of ours. He used to work for NOAA, and he was the science director at the Channel Islands National Marine Sanctuary, and so he knows all about these. He literally grew up with them in his backyard. So anyway, so we have some help here. So I mean, just to motivate this, kelp forest ecosystems have captured both the public and the scientists' attention for a long time. Right, here's a birthday cake. It's been decorated to look like a kelp forest ecosystem. And this is just a quick image quilt put together where you just search for that, and what you see is lots of charismatic pictures of megafauna, but then lots of these kind of food web studies, lots of classic food web studies have been done in kelp forest. And the conventional wisdom goes like this. Here's a sort of a three-tiered system where you have otters, and you have urchins, and you have kelp. If you take away the otters, you move from this system here to one like this, where you get these sort of urchin barrens, they call them. So the urchins come through, they just graze off all the kelp. The stems float away, and then they keep cropping down the bases, so they don't ever get a chance to recover until you go in and start removing sea urchins. And I just saw something on today that the Hakai Institute published a study where they're going in and they're literally just starting to smash these urchins or trying to deal with them, so in an effort to see if they can rehabilitate them. So we're interested in these questions in general, but also sort of how these interactions are changing. And so from this massive database that we had, which had 75 different species, I think, we simplified it down to this group of functional species, and I think there's about 15 here. So we have otters as an apex predator at the top. That's essentially a separate data set. We have giant kelp, understory kelp, lots of different invertebrates here. Pictopodia is a large starfish, sunflower starfish rather, is also a grazer on urchins. And then there are a number of other fish where lots of these were grouped by what they eat. But lots of these tend to be some form of rockfish or greenling, that sort of thing. The diversity there is high, but functional diversity is rather low. So we established essentially one of these MAR-type models with these members as a food web and asked sort of how do these interactions, you can think of these lines between the nodes, change over time. Because typically what happens is we go out, we survey something for some amount of time or over some large spatial domain,
then we assume that everything is static and there's no change in the way invertebrate eaters interact with their food or with their prey, independent of, this assumes there's no difference in these interaction strengths over time, like they're independent of density itself. And we're also interested in seeing if we could pull out what these things are in lieu of these big changes that are going on in the ocean, like large ENSO events and changes in harvest and those sort of things. So this is our model, which we talked about a lot. I'm not going to spend much time on it. It's essentially the exact same way Eli set it up. So we're going to have some covariates here that are thought of as to be external drivers. There are just one-way interactions, and then we have a bunch of interaction matrix. And ahead of time, we specifically set some of those to 0. So if you just back up here, like sea otters are not having a direct effect on, actually, but they will on some others, right? Because they eat things other than urchins. But herbivorous fish are not eating planktivorous fish, that type of a thing, right? So we had to make some calls ahead of time. We just zero those out. Every time you put a 0 in, that's one less parameter you have to estimate. Okay, so as I said, this is a process with no observation error at this point, and this B is time invariant. It's static. So the two sort of things we did was, one, to add an observation equation. And typically what we've been doing in this class is often assuming that we have some log normally distributed data. That will work in some cases, but in this case, all of the data come from some sort of counts. So there are established transects that they swim along, and at certain points on the transects, there are perpendicular transects that they go out, and at each one of those intersections, they essentially are scuba divers putting down a quadrat and doing something. So you have counts, and if these counts tend to have a lot of zeros, and the log of 0 doesn't work out very well. So one possibility is people say, oh, we'll just add 1 to all of the counts, or add 1/10 of the minimum value, this sort of thing, but that's just an artificial way to make your data look Gaussian when they're not. So what we did was modify that observation model to instead assume that rather than them coming from a log normal distribution, they're coming from a negative binomial. And there are essentially two parameters in a negative binomial, which are essentially the mean and the variance. You can think of them that way. And so the mean here is going to be our state in the equation. So this is the x's, and we're going to relate the abundance here through the rate this way. So it's this u ends up in this equation. P and R are correlated, but you end up sticking those in there. So now we can actually, the data can look like 1, 2, 10, 1,000, that sort of thing. And then we have to put in an offset to essentially account for the area that's surveyed, because some of the quadrats were 1 meter by 1 meter, others they swam something, and we're assuming 1 meter on either side, so there's different effort, and you have to control for that accordingly. So then the other bit of this is we want the B matrix now to vary. So this is going to be like the DLMs we did before in a highly multivariate sense. So you can imagine vectorizing the B matrix. So instead of it being a square thing, we just take all the columns apart and stack it up to one really long column vector. And we just treat that as an autoregressive process. So the parameters evolve over time according to a random walk, just the way we have them do in a DLM.
Mark.
Yes.
For that variance covariance matrix, did you assume it was independent or dependent?
I'll get to that in just a second. Yeah, when we talk about the thing. So the data come from San Nicolas Island, which is out here in these Channel Islands. This group right here is kind of one that's set all the way off by itself. Here's the citation for the paper if everybody is interested. The data set is amazing. It's unbelievable. So what they had were 7 different sites around the island. Those are shown here, largely 1 here, 3 in the south, 3 in the west. Twice a year, they go out from 1980 to present. This only reported through 2011, but they're continuing to do it, and they've collected a whole bunch of data. So like I mentioned, right, there's almost 80 species here. We've narrowed this list down to like 15. So with respect to this model structure, in order to estimate some of that, we assume that this is an observation of one state. These are 3 observations of one state, and these are. So now we have multiple observations of a few states, which allows us to be able to come up with some identification of the variance here and the variance here. And in each of those sites, we assume that that B matrix is the same. So even though the B is evolving over time, if you're an otter living up here, you interact with urchins the same way you do if you're living down here. And we just had to make that assumption largely to get the models to actually fit. But it also makes sense because it turns out my understanding is an otter can swim around this island in a day. So it's not that unusual. And then sort of oceanographically, a lot of the storms here come from the west and northwest. So this tends to be a very kind of storm disturbed side of the island. This is a little more sheltered. And then this is a naval landing strip. And here's a bunch of areas where like Marines and the Navy like land and stuff like that. So apparently this gets very disturbed on the shoreline as well. Okay, what do we have here? Okay, so here's the time series of otters by north, south, and west. So from this plot, you can see that almost all the otters are concentrated on the west side of the island. And previous to 1987, there had been no otters on that island for over 100 years. They'd all been decimated in the 1800s for fur by farmers because they're so cute. Then in the mid 80s, the state of California was having quite a bit of problems with otters on the mainland. Problems meaning they were competing with fishermen for the most part. So the state of California decided, we're gonna conduct a really clever experiment. We're going to save all those fishermen and otters on the mainland, and we're going to take them out to the island. So over the course of 3 years here, they trapped a whole bunch of adults and a few pups on the island, trucked them out to San Nicolas. Apparently, most of them turn around and swim home. Some die from stress and this sort of thing. But anyway, it takes almost 10 years before this population it's grown. And it continues to grow is my understanding as well. So we have a time period with no otters, and then we have this time period where there's actually quite a bit of variance over time in the number of otters out there, especially by location, right? So we have some spatial contrast in the otters as well. That part of the world, just like ours, is subjected to heavy influence of the ocean, and El Nino in particular is a really strong one. In a strong El Nino year, right, you get all this warm water in the tropical Pacific that ends up running up the coast. So in a high El Nino year, the water temperature off of Southern California can be 2 or 3 degrees warmer than another, or even more so. The range, I guess, is higher. And then in strong El Nino years in the winters, they get these really bad storms. They tend to be massive disturbances. So one of the other covariates we use is the time series of ENSO. And then lastly, we know something about the harvest of urchins because there's a commercial fishery that operated out there for a long time. It was almost non-existent in the early 80s. And then people decided that they liked urchins. The Asian markets really started to take off. There was pretty heavy fishing in here. I don't recall why this is, but this was high. And then it turned out that around 2000, fuel prices got to be high enough that this was not a profitable fishery anymore, except for a few people. So most of the fishermen abandoned that because it just wasn't worth it to drive your boat all the way out there, catch a few oysters, and then drive back. Urchins. But there is some harvest that continues today. And I remember, I guess I didn't put a picture in there. Anyway, they harvest them on scuba out of small, like 25, 30-foot boats. The guy just swims around with a bag and fills up the bag and carries the thing up to the surface and gets another one and stuff. So the human urchin fishermen are very much like otters in the way they harvest these things. But anyway, we know something about these, so these are direct takes, so we figured we'd better incorporate that into the model. Okay, so we had 6 observations. Oh, I thought we had 3. Oh, we split the west side, that's right. There were 2 of those sites were different enough that we split those out. So that's what I said before. Each state gets the same B, but B changes with time. This is old enough that we're not doing any of this in JAGs anymore. It's all being done in sand. Anyway, yes, with negative binomial errors. And in fact, we have the code sufficiently generic enough now that I think there's 4 or 5 different observation models you could use depending on the form of your data. Okay, so just as Eli said, we can look at the density dependent effects and then these sort of interspecific effects. And this is just one example. So the rows here are species. So that sheephead is a large fish that's a predator on urchins, and urchins are a predator on kelp. And the columns, first through fourth column here, are the different sites along the island. So I guess it was in the south that we split those into two different states, and that must have been because of the disturbance of one of them. The dots are the raw counts, and then the line is the Mars estimate of what that is sort of a mean count would be, with some confidence intervals above it. And there's some, I mean, you hardly need statistics for some of these, right? Where urchins here are just crashing out. You can see the kelp is just starting to explode and these sorts of things. There's some other evidence where there's some smaller scale peaks in there. This is the strength of density dependence. So this is that value down the diagonal. And what you can see is it's not at all static. Right? I mean, there's can be some really big changes in the strength. So here would be really strong density dependence. Here it's very weak. Strong, in fact, here would suggest they're like at a random walk over some of these cases in time. And typically what happens is because you get really massive increases. So this doesn't look at all like a system under density dependence. The population is just skyrocketing. So it looks like almost exponential growth here, right? So the model was thinking, well, they can't have that strong density dependence, so it's got to light up like this. Others, right, here's relatively strong, then it's released to some extent. Here's probably a case where for the most part, this is probably statistically about the same for sheephead, but they're rather mobile. These can move, but not very much, and these don't move at all. So you have to think about some differences that way. Here's two examples of off-diagonal interactions. So here's an example of a top-down interaction. This is the effect of red urchins on kelp. It's negative. That's a good thing. But here, not much evidence that it varies a lot over time. Here's an example of a bottom-up. So this is the effect of some number of inverts on things that eat invertebrates, and it's positive. And in this situation, when we actually go through and analyze, most of these look the direction they should. There are a few surprises there where it's not quite clear why there should be a positive influence of A on B or negative of X on Y, but that's ecology for the most part. So anyway, I think that's it. That's all right. Here's my signal. These are fish in the kelp forest. Yeah.
Okay, so that was an example of using these types of models to understand changes in those interactions. And this is relatively new, that people have been looking at a time-varying bee. So there's a few different approaches to that now, and the approach that Mark showed is a really nice approach because it's using this DLM approach, and you allow all the variables in that B matrix to change as a random walk. Okay, so I mentioned that the B matrix also tells you something about the stability of the system. So let's talk a bit about stabilities in these multi-species systems. Okay, so we have, when we talk about stability, we have to talk about, again, that stationary distribution, and because that's what, when we talk about perturbations away from something, we're going to go perturb away from the stationary distribution. So that stationary distribution has a mean. It has a mean. Each species has a different mean, and then it has a variance-covariance matrix. And this is the variance-covariance matrix of all the species. So if they have 15 species, that's this 15-dimensional variance-covariance matrix. Kind of a complicated thing, but we can work that out mathematically, what that should look like. And then we can think about a lot of different ways that we could measure the stability of a system. And I'm just going to pick 3. In the Ives et al. 2003 paper, which is like this iconic paper in this literature, they list, I don't know how many, lots more than 3. But these are the 3 that I'm going to focus on. They're ones that are fairly commonly used in different papers. So one is, let's start with the middle one. That's kind of the easiest one. Return rate. So you perturb the system. How fast does it return back to the equilibrium? Reactivity. How when you perturb it, how easily does it move away? Do you have to really give it a pretty good smack? Or do you just sort of a small change and the whole thing just goes, wow, blows up and does something different for a while until it returns back to equilibrium? So let's start with the return rate. So here's a little cartoon of how you might think about that. And so this really steep-sided bowl is a cartoon for highly stable. You move it out to 1, and it comes down quickly back to 3. That's rapid. And versus this one would be less stable. You move it out here, kind of the bowl is flatter, and it moves down more slowly. Well, we can measure that mathematically, this idea of how fast does it return to the stationary equilibrium, and do a lot of math. And the rate of return to the mean is governed by the maximum eigenvalue of that matrix, of the B matrix. Key thing here is that the only parameter that's appearing here is B. The rate of return to the variance, right? So there's 2 things to that. There's a mean. That stationary distribution has a mean, it has a variance. You need to return to both of them. The rate that it returns to the variance is the max of this Kronecker product. Don't have to worry about the exact mathematics here. The point is that the only parameter that's showing up here is the B. So if you just had an estimate of that B matrix, you have an estimate of how fast the system would return to equilibrium after a perturbation. Reactivity. So that's this idea. You start here, and you give it a kind of a ping, a force. A big storm comes through, wipes out 50% of your top predator. How does the whole does it react like dramatically, and lots of the abundances change, like in this case, or does it have low reactivity? And that concept, reactivity, lots of math here, but the point here is that you can kind of translate that notion into a mathematical form of that idea, and then figure out that that reactivity is again measured by the B matrix. So all these other other parameters, only the B here, but the other parameters like the variance, so the Q doesn't show up in this. So the key thing is the B matrix. Okay, and variance comparison. This is a different way to quantify the variance of the system. The point here again is that the parameter that's important is the B matrix. And it's basically in pretty much all of these metrics, it's that B matrix that is quantifying the stability.
Actually, I want to interject.
Yeah.
this, so the first one there is just basically right in this multivariate space. This, when the system is perturbed, you can think of it as this n-dimensional balloon that you're going to blow some amount of air into. And in some systems, a balloon has a very elastic, which will stretch like crazy. In others, it's made out of titanium. It's not going to move much at all. And the first one there is just mentioning how much variance you get along those different axes that all represent each of the different species. The second one here is measuring how the proportion of the total variance in the system that's owing to species interactions. So remember the last time we talked about, so you can imagine like there's two people fighting and they're standing here on this table or in this room doing it, the table's not going anywhere. And all we're caring about is they're up or down displacement. Well, at some point, one of them is going to get knocked out and fall over, so they fell 6 feet. But now imagine that fight's happening on a roller coaster, where it's going up and down all over the place, and we want to measure their total displacement. They may have gone up and down 50 feet, but only 6 of that is owing to any of their actual interactions. So that's what the second equation is doing there. And it's funny because I've actually gone through and looked at this for a lot of different systems. Almost always, the proportion of the total variance owing to species interactions is 1%. So in most of these systems that we work in, it's the process variance. There's something about the environment that's throwing that community all over the place, and it's not really the way they're fighting with one another that's doing it. And we'd have to put all these into a vacuum to try this to really know. So experimentally, I think that would be something interesting to do sometime. But yeah, and then this little trick that Ives et al. Show where you raise this value to 2. It's essentially the geometric mean of that, where they're dividing by p. Allows you to look at systems where the number of players is different. P is the number of players here. Those numbers, because you're taking a geometric mean, make it look like it's the orders are like, oh, 20 to 30%, but it's scaling. It's really telling anyway that when you actually go through and do this. So most of the up and the down, the displacements you see in abundance can, very little of it can be attributed to the way the species are interacting.
Yeah, and that brings up a key point about these studies is that when you're studying the stability, is that this allows you to separate a system that looks like it's highly variable, or sort of infer the stability of these systems where one is in a highly variable environment, so it's moving all over, and another is in a non-variable environment. It's not, changing very much. Now, well, how on earth do you compare the stability of these systems? Because clearly one is being driven by this very variable environment. But if you can estimate the B matrix, that gives you insight into the intrinsic stability of the system.
I have a quick question about the B matrix. So you mentioned that you can zero out elements of it.
Mm-hmm.
Is it all elements where you don't have like a direct prey-predator interaction are zero?
That would be.
So it's just like
Yeah, so the idea, right, yeah, so you draw your food web out on the whiteboard, and then you need to make the B matrix reflect your arrows. Yeah, so if they're two-way arrows, then you should have complementary units on both sides of the diagonal. If it's one directional, depending on which way the arrow is pointing, it would be in the upper or the lower
part. But if you have two
there.
species like compete super highly, but that would still be zero for the interaction between those two species because of the indirect effects rather than direct ones.
Oh, no, sorry. You would want to estimate a direct effect between them.
Even though they don't directly predate on one another.
Yeah, because your competition is thought of as a negative effect.
Okay.
So if you had A eats B or C and those eat D, B and C, you would still infer a negative effect between those because they're competing.
You could have indirect competition though.
Yes, but usually we typically would just directly code that, looking for the idea that you're expecting a negative effect between the two competitors.
So how would you zero out elements of it then? Because theoretically it's a big, huge mess and you could have indirect effects.
Right, so yeah, you have to decide if you want to do that. First of all, if you're going to try to interpret all of the indirect effects or whether you'd rather just interpret the direct effects, and it's usually a lot easier to just deal with the direct effects. So in my example where you have 3 trophic levels and you don't want the top one to eat the third, then that entry in the B matrix would be a 0. Because you're really thinking about these as direct effects. The topology of these is such too that, to the best of my knowledge, no one has done exhaustive. I don't think there's always a unique solution, and that your starting conditions may determine where you end up. Because this is a massive multiple regression, and if you have as soon as you make this really high dimensional, you can imagine subtracting 1 over here is about the same as having 1 over here, and maybe those 2 become complementary. When you simulate these systems and start to try to make them big, you get messy. You don't always get good convergence answers and those sort of things. So, like we've been saying for the last 10 weeks, mostly try to keep it as simple as possible. Still, so yeah, because like the example she showed of that work that Stephanie did on Lake Washington. Yeah, I mean, that was a pretty rich food web we started with, and then we pared it down to something else. And there's still some things in there that are kind of like, really? I mean, a lot of them totally made sense in the lab studies that have been done. Backed all of that up. It really was a nice way of telling a really holistic story just before it met all these little pieces of parts. So it was nice to be able to do that. But there's still going to be some head scratchers. The Kelp forest stuff we did, it's sort of like, what does this mean? It's kind of nonsensical. You can think of it again, there's that whole variance partition, right? You've got something on the left-hand side of the equation and something over here on the right. The total number of variance is the same. So as soon as we start breaking up all these pieces, the counting still has to work. So subtract something somewhere, we have to add it somewhere else. Yeah. As soon as the system is really complicated, then it can be hard to figure out exactly what you do.
And I will, at the end of this lecture, which given the time, I'll finish on Thursday, first thing, I'll talk about search algorithms. So how you search through the B matrix and set the zeros. So generally there's a initial phase where you make a decision to fix some interactions to 0 before you start, because, okay, your planktivorous fish do not eat these other fish. Okay, so you know that that's the case. You know they're not competing, so you set that to 0. The final stage is you're doing a search to determine which are the non-significant interactions that you can set to 0. And there are various strategies of for that search. It's kind of similar to your like your stepwise variable selection that you run into with these large multivariate regression problems.
I mean, I guess the other approach, Mark and I have another paper that we saw. I still need to resubmit, but you put really strong priors on the elements of the B matrix so that you give the Bayesian setting, you give a lot of weight to 0, and in that sense, there has to be a lot of data support for it moving off 0, and so in that case, kind of a way of implicitly doing that same search just in one step.
Right, yeah. Okay. So I'll finish off with one more example. The study came out of a group that we work with. This was led by Tessa, and looking at the Lake Washington plankton community. And this is another example of looking at a time-varying B matrix, taking a different strategy, though. Instead of having a B matrix where all the elements of B are this random walk, so like a DLM, instead of doing that, we broke the time series up into these windows of periods of 84 time steps. This was weekly or biweekly data. And then we analyzed the data in these different windows and then estimated the B matrix for each window. And this is what was going on during that period. We had our diatoms and green algae here. Then we have this oscillatoria here. And then remember, that was really high. And then they turned the sewage off somewhere around in here. And then after a while, these dropped well down. And then we had our Daphnia that were very low before, and then at some point after the sewage was turned off, they, their abundance became high. And same as Mark was showing in his study, what we see in this is changing interaction strengths over time. As this system is changing, the effect of Daphnia on the other non-Daphnia cladiscerans changed from having very little effect to having a strong negative effect. So this is a competition effect, right? They're not eating them, competition effect. And then the Daphnia's effect on the diatoms and green algae, that one, in contrast, is not having, not changing quite as much. This one is the really dramatic change. So we're having the strong change in the competitive effect. And then the question was, okay, if we look, that's just one example. All these interactions were changing. Can we then turn and use that information to say something about the stability of this plankton community in Lake Washington? And this is one example. This is looking at the return time metric, which is measured by the maximum eigenvalue of that B matrix. Above 1 would be unstable, and as this gets smaller, it's more stable. And what we see is that right after the sewage is turned off around here, the system goes through a period of very unstable. And then as the Daphnia come in, increase in abundance, the system becomes more stable.